Hello, my name is Cedrik Schüler and I'm a research assistant at the Communication Networks Institute at the TU Dortmund University. In this talk I'm going to present our work on the quality of experience evaluation of real-time remote operation with network constraints in a system of systems approach. First I'm going to talk about the application fields remote operation offers. In the telemedicine context, it can solve poor medical infrastructure, for example in rural regions. The industry will benefit from remote operation by a high grade of edge automation, safe machine control, and, as we all experienced during the current pandemic, a working from home. Last but not least, we have the rescue robotics field that can extensively use unmanned explorations to, on the one hand, have a safer operation for human personnel, and on the other hand, have a large-scale option for maritime rescue missions to find shipwrecked persons. Teleoperated driving is a much discussed V2X use case and can be seen as an enabler towards fully autonomous driving. It allows the integration of expert systems to take over in unknown situations. As shown on the right, we have, for example, the mission center located down below here and the remotely operated vehicle on the street here. The autonomously driving vehicle comes into a situation where it doesn't know how to behave and asks for help in the mission center. Enabled over a 5G network in between, the remote operator can now ask for the video feed from the vehicle as an input and send according telemetry data to steer the vehicle out of the unknown situation. The performance evaluation of such systems mainly focuses on the quality of service parameters, which are, for example, the packet loss, the latency, and the jitter. In this work, we want to point out the view on the quality of experience, which is the description of the end-to-end relations with a certain quality of service level and the application-specific needs. We want to answer the questions: what are the effects of network constraints, and to what extent is the application still usable? The rest of this talk is structured as follows. Next, I'm going to talk about the impact of network constraints on the remote operation. After that, I'm going to present our system of systems approach for the quality of experience evaluation. I'm going to present our case study on teleoperated driving before giving a short outlook and conclude my talk. To understand the impact of network constraints on the remote operation, we have to view on the overall system. Here we find a remote vehicle on the one side and a remote operator on the other side. These two parties now want to interact with each other. As we mentioned earlier, we would normally enable this over a 5G network. So we have a downlink traffic that is used for the telemetry data, so the steering commands from the remote operator to the vehicle, and in the uplink direction the traffic is mainly shaped by the video feed that is being sent from the vehicle to the remote operator. As we are using a real network, we are aware that we will have some network constraints. For example, as annotated here, we will have a downlink latency and an uplink latency. The system can also be regarded as a closed control loop, because the remote operator will take an action and wait for the visual input from the vehicle to assess its previous action and take the next one. So the latency can also be seen as an addition to a total latency. Also, regarding to the 5G Automotive Association, different quality of service requirements are set. The latency, for example, ranges from 10 to 200 milliseconds, whereas the data rate ranges from below 1 megabit per second to up to 50 megabits per second, depending on the link direction. A deeper look onto the requirements also reveals that these refer to speeds between 8 and 50 kilometers per hour. This indicates that the requirements are very dependent on the complexity of the scenario, which again leads us to the question of the quality of experience. Our system of systems architecture for the evaluation of remote operation follows a modular design. We have an operator side on the left and a vehicle side on the right. The components here are highly interchangeable. So for example, for the telemetry data here, we can have ROS implementations, MQTT-based implementations, or more generic protocols. On the left side also we find our mission center, which was in our case a setup with a steering wheel, pedals, and a first-person view on the display. On the right side we can find diverse operating systems, which enables real robotic test drives, reproducible simulation runs, or hardware-in-the-loop integrations. In the center we find our transmission with a network and channel module. This can be connected cabled over an Ethernet connection to the both sides or wirelessly over, for example, 5G. In order to add interferences like latency, packet loss, or channel models, we also find either channel emulators to apply real physical interferences or software like TCNetM to controllably enable the simulation of latency and packet loss. To complete our architecture, then we find our joint quality of service and quality of experience monitoring unit here, which gathers data from the other components and allows research on the interdependencies between the quality of service and the quality of experience. Our joint quality of service and quality of experience analysis in this work focuses on the network-related components. So again, if we have a look at our architecture here with the remote vehicle and the remote operator, we mainly focus on the uplink directed video feeds as the main contributor to latency. The components here can be thought as shown in the figure. So on the left side here we have an encoding unit, on the right side we have a decoding unit, and in between there is the network contribution to the latency. Before we step over and assess the impact of network constraints, especially in regard to the latency, we want to assess the contribution of the non-network components. To do this, we shortcut the network latency contribution by having a cabled setup with far below 1 millisecond of latency. So the overall end-to-end latency in the uplink direction here mainly consists of the encoding and the decoding latency. We then evaluated this by testing several video encoder settings. We did this by displaying a millisecond granularity timer on one display. This then was streamed over the video with the considered configuration to another display, and due to the latency that occurred, the other display showed some outdated information. We then captured both displays with an external camera, and the difference then leads to the results that I'm going to present now. On the left side of the plot we can see that the baseline and even the very fast setting approach of the H.264 encoder shows latencies far above 500 milliseconds, which is fairly unsuitable for high-speed scenarios. If we further tune the video encoder to the zero latency setting, which for example means the explicit ban of bidirectional frames to avoid buffering, we can achieve a 60 milliseconds end-to-end latency for the non-network components. This is also the configuration we selected. We also defined a methodology for the quality of experience evaluation for remote operation systems. We had 10 test drivers and asked them to drive 3 laps each in a racing simulator per configuration of network constraints. We applied the network constraints in a randomized order without prior knowledge to the drivers and performed this in isolated evaluation setups. So we either applied a latency constraint or a packet loss. For the latency values, we orientated ourselves at the 5GAA report, where they reported latency values between 0 and 200 milliseconds in the shown steps. And also for the packet loss values, we have loss values between 0 and 1%, which correspond to service level reliabilities above 99%. And we extended this evaluation to 2.5% and 5%. We then captured performance indicators, which can be divided into 2 categories. The first are the objective ones, like the lap time, the number of collisions, and the number of off-track situations. And the second are the subjective ratings as a mean opinion score, which is a rating between 1 and 5, where 5 is the best value and 1 is the worst value. And here we asked for questions. First on the video quality, how good was the overall video quality? Then regarding artifacts, how well were the geometric details displayed? Then stuttering, how frequently did stuttering occur? And then the usability, how good was the overall usability? This way we got tables like this for each driver, where we had our constraints that were applied, our objective and our subjective performance indicators, and these then led to the results I'm going to present in the following. So first we analyzed the impact of latency constraints on the remote operation. As shown in the results here, we can find that there is not much difference between the native environment and a setup where no network constraints were applied. So the native environment means a direct steering in the racing simulator, and 0 milliseconds of latency constraints means that there is no constraint contribution by the network. But just to keep in mind, this means that there's roughly about 60 milliseconds latency due to the encoding and decoding part. If we then further add more latencies, we can see that the lap times are increasing, which means that the driving performance is getting worse. Similar results are shown for the number of off-track situations with latency constraints, where we see an increasing occurrence of those track violations. Interestingly, for the number of collisions, we can see a consistent capability to avoid these collisions, which means that certain latencies are still quite good handleable. But as we can see here, the latency constraints overall show a negative impact on the driving performance because it's disturbing the action and reaction control above the driver, which in turn leads to timing problems and therefore leads to less accurate driving, which can be seen also here. But as the 80 millisecond setup, for example, shows, it's still possible to maintain a safe operation if the driver is driving slower, as we can see here with an increased lap time of roughly 6%. Next, we analyze the impact of service level packet loss. Here the results look a little bit different. So we can observe that there is a slight increase in the lap time between 1.9 and 2.4% for the lower packet loss levels, but only if we step over to the 5% packet loss, we exceed the frame compensation capacity of the decoder and observe an increased lap time of 26%. Also, as it can be seen on the box plot here, the driving performances are not very consistent anymore. The results look quite the same for the number of off-track situations and the number of collisions. So a packet loss can cause massive performance deteriorations above a certain threshold, which is encoder and decoder specific. So here we find an interdisciplinary trade-off between the robustness of the video encoder and the latency constraints that can be still compensated. We then analyze the objective quality of experience ratings. Again, as a reminder, these were the questions we asked the drivers after the respective drive test. And as we can see on the results on the right, the ratings for the applied network latency are shown in blue, and the latency has no effects on the video quality ratings, as we can see here. And also this holds for the artifacts and the stuttering. This is different for packet loss, where we have progressively worse rated video quality, for example. And as we can see here for the artifacts, more and more frames were lost. And especially if an iframe, so a full image, was lost, then the drivers more or less had to drive blindly for a certain amount of time. We can also observe a linear impact of the packet loss on the stuttering, because always when frames were lost and the time causality was not given, this occurred as a stuttering to the driver, so this was just as expected. For both types of constraints, we can see that the usability is getting worse with more and more latency constraints and packet loss constraints, which means that there is an increasing stress that makes the drivers more exhausted. And interestingly, here we can see that it's worth looking at the subjective as well as the objective parameters for quality of service and quality of experience, because here for the packet loss, for example, we can see that there is quite a similar performance on the objective parameters, here in this case the lap time, but we have a significantly worse subjective rating here. I am now giving a short outlook based on our system of systems architecture. First, it is possible to have a dynamic testing of demand-based network configurations. Especially in private 5G networks, the operator can now test different network configurations and directly see the impact on the quality of experience of the installed applications. Next, it is possible to integrate robotic systems into our architecture. As shown on the videos on the right side, we were already able to integrate small-scale vehicle platforms into our architecture, and this will have a 5G-based remote operation setup. Furthermore, it is possible to evaluate the quality of experience requirements for different platforms, so there may be differences between aerial and ground-based vehicles, as well as these requirements may be different from typical driving applications or fine motor tasks like they occur in telemedicine. I'm now going to conclude my talk. In this work, we proposed a system of systems architecture for the combined quality of service and quality of experience evaluation. We followed a modular design to allow a seamless swapping of several components. In first drive tests, we demonstrated the end-to-end impact of network constraints on the remote operation. We show potential for extensions, so for example hardware-in-the-loop integrations, or as mentioned on the slide before, scenario-specific network planning for quality of experience-aware optimization. In future work, we will transfer the system to various operating environments and integrate so-called radio environmental maps, which contain spatial network and channel information, and therefore allow the quality of experience evaluation in consideration of real mobile network KPIs. Thank you for your attention. If you have any questions, feel free to ask them or to contact me via email.